timekeeper.
Changed my name and everything.
Hello and welcome back to Calculus 1. So right now 4.8 is a section on approximation again, but this time we are using this approximation to calculate the root of a function. You see that certain functions are easy to solve algebraically, but then they're hard to compute. Other functions are hard to compute, but to find the root is living nightmare. For instance, polynomials are like that. We love polynomials. Easy to differentiate, easy to take the limit. You will domain all real numbers, right? Easy to compute when you plug in the value. You will see also that integration, which is coming up very soon, is very easy for polynomials. Everything is easy for polynomials, except when you have to find zero. And that is a living nightmare, to find a zero for a polynomial. Because polynomials have very simple x and y intercepts, right, for linear lines. Quadratic formula will give you the roots when you do the, the negative b plus minus square root of, right, b squared minus 4ac over 2a. That will give you roots for quadratic. There are formulas for cubic. There is a procedure that takes about 2 hours for fourth degree. And then there is a mathematical proof that you cannot come up with a formula or a procedure to find roots for polynomials of order 5 and higher. So it starts very easy with the x and y intercepts, right, or x intercepts, to find roots in a linear line, which is the function polynomial of the first order. You just have mx plus b, right, so x to the first power. The x squared is the quadratic formula. X cubed is already, formulas are in two rows, 3 of them, right, for 3 solutions. And then finally, the procedure for the four roots is horrendous. I spent 2 hours calculating. The first one got it wrong, and I just said, you know what? Video game time. So what we have now is the method, Newton's method, right? Self-explanatory, to find roots of the function. So how does this work? It has a very interesting method to it. So let's say that you have some function, f of x, and this is the unknown, I'll put a, unknown root. Root is where the function hits the x-axis, or goes through it, right? Now you will pick the random close by point, and you will find the tangent line at that point. Observe that tangent line cuts the x-axis. You use that x to come up with the new tangent line, and then you have the new tangent line, and as you are going, the tangent line will eventually start cutting through the point in question. It's a very interesting idea. It works great. So now we just need to write down, understand the formula, and do the example. Now these things are programmed into computers. These things are to program in your calculator, and because you really don't want to sit there and spend 30 minutes on calculations and 20 seconds on concept, right? So yes. Well, we can't have the derivative 0 because in the denominator, you will see now. So what is the formula for this? So number one, well, let's write this as a procedure. Number one, pick a point on x-axis close to the root. You are trying to find. And that point, call it x0. That's the first one. Number 2, for n equals 0, 1, 2, 3, going on. Here's the formula. The next n value, next x value to compute this whole thing in is the current value minus the function computed at xn divided by the derivative computed at xn. And now you see why the flat pieces don't work. First off, if you have a flat, it's not x-intercept, right? And the other thing that you should think about is also that when you have a horizontal slope, which is slope of horizontal line, then the slope of that line is 0, and that will just kill the entire process. Right? So let's see if we can master something nice here. This is terrible enough. Number 16. It says f of x is equal to e to the x plus x minus 5. And they say initial guess use 0. No, I'm doing 16, right? 1.6. x0, first guess. So what do we have here? Well, we need the derivative. So f prime of x is just e to the x plus 1. So we needed that. And now what you're going to do? Start computing. So you already have x0, which is for n equals 0. So the next one is n equals to 1. When n is equal to 1, yeah. Oh wait, we compute for n equals 0 first. Sorry. N equals 0. So when n equals 0, you get x1 is equal to x0, which we have, minus f of x0 divided by the derivative computed at x0. So your job is to plug these values in. So x0 is 1.6 minus, and now you have the function computed at 1.6. So function computed at 1.6 divided by the derivative computed at 1.6. So x1 is equal to, we have the function, so now you can use your abacus to figure these values out. We have 1.6 minus division line, right? So we are going to do now function computed, so that's e to the 1.6 plus 1.6 minus 5 divided by the derivative, which is e 1.6 plus 1. As you can see, this is going to give you new value. So clear everything from the calculator. Let's go. Everything in one shot. So 1.6 minus open parenthesis e raised to the 1.6 plus 1.6 minus 5 close parenthesis divided by open parenthesis e raised to 1.6 plus 1 close parenthesis, and that's it. So now we got the 1.339. Well, 1.34 because it's only one decimal on the original. So now for n equals to 1, and the computer science student in this class go, please, no, we can just write the loop. Please do. Write the loop. So what do we do now? We go and say, for x is equal to 1, you have x2 is equal to x1 minus function computed at x1 divided by the derivative computed at x1. So just now, instead of using 1.6 everywhere, you are using 1.34 everywhere to calculate the better value. So x2 is equal to 1.34 minus the function of 1.34.
That's the same derivative. You don't take the second derivative.
No, same derivative throughout. It's just one formula. F prime at 1.34. So the only thing that will change is the number, because you go use different number. Everything stays the same. It's very tedious, but such is life. Yep. Minus 5 divided by e. Oh, I forgot a minus here. Divided by e. Well, what's going to happen? Well, you know which precision you want, because this thing gives you a lot of decimals. And then as you go on with this calculation after n equals 10, 15, 16, 17, right? What happens is that the digits start being pinned. So you see that we went from 1.6 down to 134, right? Eventually, we are technically, 1 is pinned already, right? 1 point is pinned.
Okay, so
And then the more of these iterations you do, the more of a number becomes pinned. So if you need 6-digit precision, you will go until the 6th digit is, yeah. So this is why you do this with a computer.
so how far you want us to go on these now?
What exactly? What are you talking about? We're not. No. All right, good. That's it. That's the Newton's method. Bye.